from some alumni, and we've spent a lot of time cutting rocks and collecting rocks. So if you guys want to come, all of the proceeds are going to go to next semester's activities. So towards a good cause. Any questions? Okay.
Just come, right? That is the only thing we need to do. Any other announcements from students? Okay, awesome. Just let you guys know, not long ago, Jan left for another position. Our academic advisor left. So now Mandy left yesterday for a new position. Don't worry. No, it's good, very good. Everything is under control. The other advisors, they're not really specific for our department, but they are really willing and happy to help. So don't hesitate to reach out to any advisor at this point. And also, I'm very happy to meet with you guys. And also, if you are familiar with some faculty members, feel free to reach out to them. We're all here to support you. You are not alone, right? So, you're back from the break. Let's power through the last few weeks. Any specific questions for me? So we do have a new advisor. She is still in training. She is not really accepting appointments at this moment, but if you do reach out to her, I'm sure she will reply and give you some suggestions. Like we met yesterday to discuss the transition period. Don't be afraid to just reach out for help. That is very important for you to reach out, right? Any questions? Underline, don't worry. You are the senior now, so you need help. So we do have like a student, Earth Science Student Association. That is your group, your community. So make sure you're part of this association. They are very experienced. They can provide you more information than I can do. So reach out to them, okay? And then we have Emmeline here. Can you guys stand up just to introduce yourself quickly?
Introduce ourselves?
Yeah, for the association.
Okay, so my name is Emmeline. I guess I am a senior, but I'm in the presidency for the Earth Science Student Association.
Oh, I'm Haley. I'm a junior, also in the presidency.
And I'm Dylan. I guess I'm a senior with Emmeline too. Also in the presidency.
Great.
Yeah. So I guess I'm Dr. Tokay, so welcome to the seminar today. Are there anything the seminar leads need to say about the end of the semester?
No, I'm passing around the attendance sheet.
Okay. So do the attendance sheet. There's one more seminar, right?
There's one more seminar. The faculty don't need to come.
Oh, it's
It'll
students
be
only.
a debrief.
So it's kind of good for the search
Okay.
committee to meet.
Okay, great. Yeah, so well, I guess I was going to say we're the penultimate group of speakers, which is like an earthquake term for second to last. It's used other places as well, but I guess we're the last speaker group of the semester, so thanks for having us. So yeah, I'm Dr. Tokay, and today my students and colleagues over here are going to tell you about different applications of LIDAR, light distance and ranging data, to study topography and past earthquakes and subsidence of the land due to pumping of groundwater. Okay, and so this is all kind of in preparation for some talks that they'll be giving at this upcoming meeting in 2 weeks at the American Geophysical Union in San Francisco. And so it's going to be like tens of thousands of earth scientists there all at once. So it's going to be really exciting for them. We'll get to share our research and learn a lot. I'm going to introduce a couple of slides, introduce them, how they got through their projects, and also give a few advertisements. So one is, if you're interested in this type of data, LIDAR, a great resource for you would be opentopography.org, which is a great place to download these types of data sets. And then also this national USGS 3D elevation program, or 3DEP program, another great resource. You can find a lot of that data on open topography. As we go through, we're going to hold questions till the end because we do have 3 mini talks and we want to get through them all. We will have pizza afterwards in the usual room, 223, so if we run out of time for questions, we can go there for questions. Okay, so we're going to have first a talk by Veronica and Parker here, and they're going to tell us about their project, which was funded by UVU's ERSCA program. I can't remember what that exactly stands for. It's Undergraduate Research, Scholarly, and Creative Activities Awards. And so they were able to fund their time to study the Nephi segment of the Wasatch Fault using LIDAR. And then David Munsey is going to tell us about ground subsidence that's going on near Cedar City in southern Utah, and that's using 2 different LIDAR data sets and subtracting them with time. And that project came about not from a funded research project, but from a class project in advanced GIS. So it's a great class to take, GIS 3650. David's project is going to be, David Johnson, is going to be talking about the Thousand Lake Fault, which is this fault way on the edge of the Great Basin here. It's really kind of in the transition zone to the Colorado Plateau here. And all these projects are right on this edge of the basin and range. So they're all related to kind of normal faults, creating these downdrop basins filled with sediments, alluvium. And so think of that as you're going through what they're telling you about today. It's important. And so, yeah, everybody's using LIDAR, but we're using what's called interpolated LIDAR, so digital elevation models. As a native data set, LIDAR is a point cloud. Basically, you fly or you collect data with like a pulse of light passed across the landscape and get reflections, points back. But you can interpolate that into a grid, and so that's what they're using here. And they're using classic programs for GIS, ArcGIS Pro, ArcMap, QGIS, and then applying MATLAB and some other things as well. Okay? So they're going to be doing some mapping of faults, profiles, and differencing of DEMs. And so I'll stop there and turn the time over to Veronica and Parker. Thanks.
Hello everyone, I'm Parker Farnworth.
And I'm Veronica.
And for the last year, like Dr. Toke said, we've been working on an ERSCA grant-funded research project using LIDAR to measure vertical separation of Holocene landforms and map slip distribution along the Nephi segment of the Wasatch Fault. So as Dr. Toke had mentioned, and to give a little bit of background, our project finds itself right at the edge of the Basin and Range physiographic province. So the Basin and Range, like the name suggests, is dominated by these repeating mountains and valleys. Most of them are trending north to south. And this pattern is caused by extensional or tensional stress that is stretching out the crust in the area. This causes the formation of numerous normal faults. So normal faults, as can be seen in this diagram right here, have a footwall that moves up relative to the hanging wall, and as time passes, the footwalls form mountain ranges and the hanging walls form large valleys. And the Wasatch Fault, which is the fault we're concerned with, forms the northeastern boundary of the Basin and Range physiographic province. So the Wasatch Fault is the longest active normal fault in the United States. It runs nearly 400 kilometers from southern Idaho to central Utah. It has been divided into 10 segments based on paleoseismic investigations of prehistoric ruptures. The researchers have decided that 5 of the segments should be considered highly active. Those are the segments that are in red here in this chart, and that 5, the end segments in green, should be considered to be less active relatively compared to the central segments. The Nephi segment is the southernmost of the active, highly active segments of the Wasatch Fault. And we've been researching specifically the Nephi segment as populations of southern Utah County and eastern Juab County expand rapidly. It's becoming more and more important to understand the seismic hazard to see what risk the Nephi segment presents to the population in the area.
Okay, next we just want to quickly remind everyone what a fault scarp is and talk about slip distribution. So a fault scarp forms when there is a seismic event or an earthquake of a magnitude about 6.5 or higher, because at that magnitude the event will rupture all the way to the surface. The top left picture is a photo of a fault scarp that is part of the Nephi segment. Within the white rectangle, you can see the shaded area is the scarp face, and the areas above and below in the sunlight are the top and bottom geomorphic surfaces that have been offset. Also, a fault or fault segment doesn't have the same vertical offset along its entirety. It breaks differently in different places. The way that a fault breaks in a single earthquake is called the slip distribution, and the expected slip distribution for a single event is that there will generally be more vertical offset at the center of the break than at the edges, meaning that the measured vertical offset along the entire length that broke at the surface will form an arc shape. So this figure on the side shows 3 possible ways that a fault segment might break during a single event earthquake. Our overall goal has been to study the slip distribution of the most recent earthquakes on the Nephi segment. As part of that goal, we wanted to make a figure like the one shown here, which graphs the vertical offset by the distance along the fault and maps the hypothesized prehistoric earthquakes. This figure shows 2 of the most recent prehistoric earthquakes along part of a fault in Idaho. The one in blue is the most recent prehistoric earthquake and has less cumulative vertical separation, and the one in pink is the penultimate earthquake, which has slightly more cumulative vertical separation. So in order to reach these goals, we needed to measure and organize our data. We needed to add data from previous trenching studies which were done along the Nephi segment, and that will give us a frame of reference and help us supplement our own data. We also needed to look for patterns that would help us determine the rupture scenarios of past earthquakes, which is mainly looking for that arc shape. And then finally, we needed to try to map out the few most recent earthquakes based on their age, offset, and their expected slip distribution. Our first step in the research process was to download 1 meter Lidar for the Nephi segment from Open Topography, as well as to download a shapefile of the Wasatch Fault from UGRC and to add those into an ArcMap project. The top right figure is a slope map showing our area of interest, which is the entire Nephi segment. And then our next step was to use the profile tool in ArcMap to draw profiles across offset geomorphic surfaces along the entirety of the Nephi segment. And we drew profiles across offset geomorphic surfaces that had relatively equal slope both above and below the scarp face, because we only wanted to measure surfaces that have experienced relatively equal amounts of erosion and deposition since breaking. So this bottom right figure is one of our layouts that we created showing one of our many profiles that we drew along the Nephi segment. You can see the Wasatch Fault running from the top left diagonally down to the bottom right in green. And then running perpendicular to that in a lighter shade of green is our profile that we drew. And then this bottom middle figure labeled Maple Dell 2 is that same profile, and it's just showing the change in elevation along the y-axis in meters against the length of the profile also in meters. So that just shows you the shape of a pretty decent fault scarp that we're looking at, and you can see the slope both above and below the scarp face is pretty equal.
So we ended up finding a little over 200 suitable fault scarps that had separated geomorphic surfaces. And our next issue is we needed to actually measure the vertical offset or vertical separation of each one of these fault scarps. To do that, we exported all of our profiles as text files and put them into a MATLAB script called ScarpVS, which had been developed by the United States Geological Survey. And this was a fairly simple process that involved selecting the upper and lower slopes that we believed to be representative of the original slope of the surface, and then selecting the scarp slope, and the program would project those original surfaces out and then measure the vertical separation between the two. To reduce bias in our measurements, we ran each scarp profile through this program a minimum of 3 times. And then we chose to use the mean offset in our calculations and then use the minimum and maximum offset to define a range of uncertainty that we could use in our data. So this just shows a final profile output. You can see the blue line, the black line is representing the original profile, the blue lines are the original projected surfaces, and the red line shows the offset. In this particular case, there's 2.5 meters of offset in this fault scarp. So we can see that the upper and lower slopes of this scarp are relatively similar, haven't been modified highly, and were most likely connected at some point in the past before they were ruptured by one or more surface faulting earthquakes.
So after running our profiles through MATLAB, we brought our vertical offsets and location data for each profile into an Excel spreadsheet, as well as the previous trench data, which included each recorded earthquake's age, location, and offset. We compiled all of this data to create several different figures graphing the results. This is our first graph that we made, and it shows all of the trenching data that we got from previous studies. And it's graphing the age of each individual earthquake measured in each trench against its distance along the fault. So the way we have it set up is at an x value of 0 is the very southern tip of the Nephi segment, and then as you go farther negative, you're getting farther south into Levan, and then as you get more positive, you're getting farther north towards the southern end of the Provo segment. And we do have one Levan trench marked in green and one Provo trench marked in orange. So to reiterate, the goal of our project, it was to study the slip distribution and identify rupture scenarios for individual earthquakes. We used trench data as a reference, and we looked for patterns like the arc shape. As we did this, we had to keep several things in mind that might make it difficult to correlate offset features into corresponding earthquakes. First, if there was too much variation in slip for a single event, we might not be able to reliably determine a certain number of prehistoric earthquakes. Another issue is that some of the data, mainly the ages of the earthquakes that we got from the trenching data, had very large uncertainty ranges that made it difficult to match their offsets with each other into even a single event. And the last main complication was that we needed to consider the possibility of interactions between different fault segments, which is why we included one of the Levan segment's trenches and one of Provo segment's trenches. So this is that same graph that was on the previous slide, and then above it we have our Lidar that we've been working with in ArcMap this whole time. So on the Lidar in red, yellow, and green are just all of the different parts of the Nephi segment, the fault, and then the pink circles are marking those trenches, the Nephi trenches. And then on our chart, we're graphing the vertical offset in meters against the distance along the Nephi segment, the same way as that first chart. In yellow, again, those are all the Nephi trenches, and all the blue dots are the geomorphic surfaces that we measured the offset of ourselves. The Provo is in orange, and the Levan is in green. And there are two areas that we determined are really important that we marked on here. So the first one is marked in purple near the center of the graph, and we labeled it the step-over zone. And if you look at the Lidar up top, you can see that there are kind of 2 or almost even 3 sort of strands of the Nephi segment that run parallel to each other almost, and that just led to some complications when we were looking at our data, so we wanted to point it out as an important area. And the second area is in orange near the northern end of the Nephi segment, and we labeled that the Provo-Nephi overlap zone because you can't see it in our figure, but this is actually an area where the Provo segment runs kind of south past the northern tip of the Nephi segment, so they kind of run a little bit parallel to each other like the other area. And this is an area where we think we've seen evidence of some interactions between the Nephi segment and the Provo segment.
All right, so past authors have interpreted the Nephi segment several ways. So one popular interpretation currently is that both sides, north and south of the step-over zone, are essentially acting as independent fault strands, having their own earthquakes that rupture and then die off in the step-over zone. And this is based primarily on the paleoseismic trenching data that we were showing you guys earlier. As you could probably see in that last figure, the distribution of our little blue data points is not as clean or easy to interpret as those nice idealized diagrams. So it really helps to have our the trenching data to reference against. One big issue with this current interpretation of the 2 separate substrands of the Nephi segment is that there are only 2 trenches on the northern strand here of the Nephi segment. And the most recent event in the northernmost trench does not line up with in age or in offset with the most recent event in the trench only a kilometer away. And this by itself would suggest that there's some kind of complex faulting interactions ongoing. Some past authors have suggested, because this is an area where the Nephi segment and the Provo segment run concurrently near each other, that there could be possible interactions between the two separate segments. Here's that a little rupture scenario graph that we made, blown up larger. So here we've marked out in dashed lines groupings of our data points that we think could correspond to certain earthquakes. Here in black, we have this line running through the Provo segment. Because the most recent event on the Provo segment lines up in age and in offset with the most recent event in this trench here, they could possibly be correlated. This is supported by our data because the spread of highly offset geomorphic surfaces, that is, surfaces offset more than 6 meters, is roughly equal on both sides. And this is important because, as you can see here on the northern strand, the interpretation of the paleoseismic trenches is that each event is only offsetting 1 meter at a time, while on the southern strand, each event is offsetting 2 and possibly even 3 meters per event. And so over time, as these surfaces accumulate slip, we would expect that the surfaces on the northern strand, because we have evidence of small faulting earthquakes, that the surfaces on average would be smaller, but we don't see that. We see a fairly even number of highly offset geomorphic surfaces on both sides. And this would back up an interpretation that there is complex interaction going on in the northern strand of the fault. Specifically, a possible Provo event faulting into the northern segment of the Nephi, the northern portion of the Nephi fault. And this is important because spillover rupture, that is part of a fault breaking along with a separate segment, can influence the magnitude of that event. So a longer rupture will mean a higher magnitude for that event and a more dangerous earthquake. So if there is indeed spillover rupture from the Provo segment to the northern segment, it's very important to know about it because that would increase our calculations of the possible magnitude of future earthquakes.
Okay, we just wanted to go over a few key takeaway points before we end our presentation. First of which is that faults don't really break as simply or as consistently as we might think they do. Rather than full segment ruptures, we're seeing evidence of potentially partial segment ruptures or spillover ruptures on the Nephi segment, spilling over into the Provo segment. So it's important to be aware of that. And then another thing that we want everyone to remember is that it's important to study and learn things like this, because if we can understand paleoseismology and learn about seismic risk, then we can plan better to keep people and communities safe, especially people who are living nearby active faults, like the Nephi segment. And our last key point is that if you're interested in doing research, you should talk to one of your professors, and you should apply for ERSCA funding, because that's what we did, and it was really cool, and we had a lot of fun. We did cool research, we got paid, and we're really excited to go to AGU in a couple of weeks and present. So that's the end of our presentation, and now David's going to come up and talk about ground subsidence.
Like Dr. Toke said, I'm David Munsey, Earth Science student. And then last semester in our advanced GIS class, he gave me this project about measuring subsidence. I thought it was pretty cool, so this is what I did for my project. So it's measuring subsidence in Cedar Valley, Utah using Lidar and comparisons with INSAR. So just briefly, Dr. Toke kind of went over it, but what is Lidar and INSAR? So Lidar is a tool to measure elevation. It's a very high definition source of imagery compared to other sources such as Landsat. So for example, with Lidar, it's 1 meter resolution. So basically, I don't know if anyone's taken GIS classes, but basically what that means, if you zoom in on the map and you go to 1 pixel, each pixel is 1 meter by 1 meter resolution. And so other sources of imagery like Landsat, which we use a lot, is like 30 meters. So it's very high definition. In this example, and then also, LiDAR can be is mainly performed by satellites and airborne missions. So you can either get it from satellites, or you can like fly a plane and shoot the ground with the active radar. So for mine, this is all an airborne mission that was performed. So one flight was done September 2011, and then the other flight was done May 2020. And then also the other satellite that we were looking at, just to make some comparisons, see which one maybe worked better or similarities, differences, was INSAR. And so INSAR is just another form of active radar that measures ground movement over a period of time. So yeah, that top portion up there is going to be your INSAR imagery, and then this one that I made is going to be LiDAR. And then another thing is like, what is subsidence? So subsidence is the downward vertical movement of the Earth's surface. So basically just a decrease in elevation. So subsidence can be caused by natural and anthropogenic processes. So these processes can be such as groundwater overdraft, underground caves, that there's caves under and then subsides underneath, and then other resources that are removed from the ground. So once the subsidence has taken place, it can create the formation of earth fissures. So earth fissures are just long and narrow cracks or openings in the earth. So in my project, there are several areas that have seen subsidence. So the picture on the top right is an earth fissure in Cedar Valley. So this is actually one of the earth fissures that are in the area. So as you can tell, there's like May 6, 2009, and then 6 months later was November 3rd. And the picture I got it from, it didn't have the date, but I'm guessing maybe 6 months after that. And then the bottom right picture is subsidence. So as you can tell, the showing spikes because you can see the cement block used to be flush with the surface of the earth and is now a few feet from the surface. So down here it used to be flush, and then it subsided, and so now it's up here. And so this is kind of a brief background of what my project did, just a little background of the history. So over the past 15 years or more, Cedar Valley, Utah has seen major subsidence. In May 2009, Enoch City contacted the UGS to investigate a 2.4 mile long earth fissure that was damaging the local area. So it was determined that the subsidence was caused by groundwater overdraft of the local aquifer exceeding the groundwater recharge rates. So this certain aquifer was around an area where the soil is fine-grained and highly permeable, which promotes subsidence. So this pattern of subsidence can also be related to fault structures and patterns of fluvial and pluvial deposition. So since 1939, the groundwater surface has lowered by 114 feet, directly correlated to the aquifer depletion. So also over 110 square miles of the area has seen as much as 4 feet of subsidence. So using Lidar Differencing, I was able to see exactly how much subsidence has taken place. So in my project, so this kind of gets more what I did in my project, I differenced the 2021 USGS 3DEP from 2011 state of Utah data set. So those two things I'm talking about was what I mentioned earlier with those flights, the LiDAR flights. So in other words, I took the elevation data from the 2011 data and then subtracted it from the elevation data of the 3DEP. This was to see how much subsidence has taken place over the past 8.7 years. So the three areas in Cedar Valley which have seen the major subsidence are Southwest Cedar Valley right here, Enoch Valley, the one right here, and then we have Parowan Valley. So this is like the most south, and then you go a little more north, and this is where that is, and then even more north is where the Parowan Valley is. So as you can see from the legend, the red and yellow areas are showing a decrease in elevation, with red being the highest decrease, and then goes up to yellow. And then you have blue. So blue is an increase in elevation, and then the green is just little to no change, like no change. And the reason you see the blue is just because of crops and infrastructure. So when they flew the LiDAR airborne pass or whatever, there must have not been crops. And then when they flew it again, there was crops. So that's why there's an increase. And then you'll also see on the maps, there's two lines on each map, so you can see one going each way. Those are just some profiles that Dr. Toke and I made just to measure the subsidence rates. So this is just some, this slide is showing the profiles and subsidence rates for Southwest Cedar Valley and Parowan Valley. Each profile is showing distance along profile in meters on the x-axis, and then a change in elevation also in meters on the y-axis. And then the red line you see going through is just 0 or no change, just so you can differentiate the 0 from increases or decreases in elevation. So the two profiles taken in Southwest Cedar Valley are going through the lake. So on the top left, you'll see one is kind of going this way through the lake, and then the other one is going through the field. So the lake profile starts at the top portion of the subsidence. On that top, you can kind of see a little red up there. So it starts in the top portion of the subsidence and then heads down southeast over the lake. So this profile showed the subsidence rates were generally around 0.023 to 0.034 meters per year. That doesn't seem like a lot, you know, but it is subsiding a little bit. So then the field profile starts at the bottom of the map. So we start at the south, where you can kind of see where the agriculture is, the crops. We start at the bottom and then headed north. So this profile showed the subsidence rates were similar to the lake. And then in Parowan Valley, the two profiles taken in Parowan Valley are going southwest to northeast. So from southwest to the northeast. So this one going that way. And then the other one was going southwest to southwest to northeast, and then northwest to southeast. Sorry. So then we go in northwest to southeast over this way. And then it was shown that the southwest to northeast profile showed subsidence rates of around a similar 0.023 to 0.046 meters per year, except for an area that experienced a major subsidence rate of 0.11 meters per year. So they both kind of show the same subsidence, except this one right here that's going through maybe the darker area of red you see right here had a higher subsidence rate. And then this last one is just the Enoch Valley. So this slide is showing the profiles and subsidence rates of Enoch Valley. So this area saw the most consistent subsidence and followed the geometry of the fault structure impacting the area. So the two profiles that were taken were from east to west. So on down bottom left you can see east to west, and then one was from north to south. So the east to west profile was very consistent and saw a 0.046 meters per year of subsidence over 500 feet. So you can see from the profile right here, this has that really nice consistency of subsidence over from like 350 all the way over like 1,000 feet, meters. So overall, all the areas of subsidence were generally similar. So with all the maps, not all the maps, but all the areas, they were all generally similar, just with a few outliers. So that's kind of became that conclusion, is most of the subsidence was similar, except for a few outliers and then some consistency like this. And then just with some comparisons with INSAR, so this is just an INSAR map that other investigators performed. So the INSAR results were done by other investigators at the Parowan subsidence area. Overall, we see broadly similar patterns of subsidence. Their subsidence rates of 20 to 40 millimeters per year are comparable to our results. So basically they saw the same areas. You can kind of tell I did some georeferencing, and so this area right here is kind of like this area right here, as you can see right there. So they're seeing that 0.04 subsidence in the red, and then kind of right here, if you can see, we're kind of seeing generally the same type of rates there. And then just like some outcomes from it, so just overall, the subsidence in Cedar Valley, Utah is due to overdrafting local aquifer. The subsidence rates over 8.7 years is generally 0.2 to 0.4 meters. And just some things to combat subsidence is just avoid overdrawing groundwater supplies. So the recharge equals the withdrawal. Don't overdraft more than you recharge. Mapping and monitoring existing fissures and areas of subsidence, just using different stuff like Lidar, INSAR, and photogrammetry. Mapping groundwater aquifers in detail, so you know exactly where they're at. And then just building resilient infrastructure that won't fail catastrophically with an earth fissure. So that was my project last semester. And then let's turn the time over to the other David to talk about the Thousand Lake Fault.
My name is David Johnson. I recently graduated this past summer.
What are you going to do in January?
Oh, and I'll be starting a master's program in January at Idaho State University. So, but I've been working for a few months with Dr. Toke, who was very generous to offer me something to do over the last few months, and it was a lot of fun. So this project was derived from a mapping project that we did over the summer, and we were able to do a little bit more work on it to ultimately try to further constrain the magnitude of the most recent event. So, just a little bit about the regional setting. It's been touched on that the Thousand Lake Fault, north-south trending fault, just like a lot of the faults in the basin and range, near Bicknell, Utah. And it kind of runs along the hinge line between the two geologic provinces, the basin and range, which is this huge zone of basins and valleys that are in an area of crustal extension and thinning that's kind of driven through gravitational collapse and in part in reallocation to stresses along the borders of that province. And so, and then in comparison to that, you have the Colorado Plateau to the east, which is remarkably stable in comparison to the basin and range. And so the relationship here, not something that we covered in this project, but is something that I'm hoping to pursue in the future. Is just something I'm interested in, is kind of what's going on there tectonically. But we are in an area where mapping the main trace has a lot of geologic, let's say, advantages, but like visual advantages. If you like field geology, this is a really cool area that we were able to go to. You can see just in the aerial photography here, the juxtaposition between superficial volcanics and the bedrock underneath. It jumps right out at you. And then in the fault zone, there's lots of springs, lots of groundwater running through. Again, you can see the juxtaposition between superficial volcanics there that are tertiary in age, and then these Mesozoic packages to the right. And then all over, I think in the Navajo sandstone within the fault zone, I, in one canyon, found red, yellow, white, orange, and then candy cane is what I affectionately named it in my notebook while out in the field. So, a little bit about the geology. You have your nice Mesozoic packages in the footwall block. We can call them the national parks of Utah, like center stage rocks. You know, you have your Moenkopi, Chinle, your Wingate, Kayenta, and then Navajo, all beautifully exposed in the footwall block. And then in contrast to that, you have superficial volcanics that are mostly tertiary in age. You have them throughout the entire valley, and then on the capping plateaus, so the Thousand Lakes Mountain and the Boulder Mountain, which actually, the Boulder Mountain, which is part of the Aquarius Plateau, is the largest continuous area in Utah, over 11,000 feet. So there's quite a bit of an elevation difference. You can see in the most recent map by Beek in 2021 that there's probably somewhere around 3,000 feet of displacement that he's got in there, which is a little under 1,000 meters. But when you compare the superficial deposits from the top of the Aquarius Plateau to what's all the way on the other side of the Fremont River Valley, you get anywhere from 1,500 to about 2,500 meters. So a little bit of contrast there, but that might be due in part to the fact that a lot of the units, as were mapped in the hanging wall block, had some really varying attitudes, whereas there was pretty nicely represented horizontal units in the footwall. So a little bit more displacement there than this map shows. So mapping the main trace was great, but really the goal of this study was to map some of the more recent events. So if possible, the most recent event, but probably what this more represents is the most recent event and the penultimate event on some of the traces. And so doing that would involve the LiDAR set that we pulled. And it's a beautiful LiDAR data set. It is riddled with glacial features and mass wasting events and all kinds of rabbit holes to go down to distract you from your one project that you're supposed to be doing. So, but anyways, spent quite a bit of time in it and found that for the most recent event, 1 to 2 events, probably represent about 32 kilometers of the overall 58 kilometer fault zone, and go from just north of Bicknell all the way to the very southern reach of the Aquarius Plateau. It was important, though, with the scarps that we were able to filter out things that would be appropriate to include in the data set. So from the trench study in 2018 that Dr. Toke did, they found 2 events, both with roughly a meter or so of offset. And so I wanted to limit the scarps that I was going to include in the data set to anything less than about 2.5 meters. 1 to 2 meters would be ideal, and then 1 meter would be the very preferred. So that if there is about 2 meters, you could say maybe there's 2 earthquakes here that utilize the same fault or the same trace, and with 1 meter, awesome. And then using the VScarp script in MATLAB, it was able to give me a average slope of each one of the scarps. And so it'd be funny, I find something that was really, really compelling, and I'd run it through the software, and it'd give me a scarp slope of like 85 degrees, and I'd think, okay, that's some bedrock there. I need to go back and see that. But then anything that ranged between about 15 to 60 degrees we include in the data set. And then the best case scenario is when it's offsetting a young geomorphic feature. So because we have glaciation in the area, that gives a great constraint. There's a really long recurrence interval on this fault. I think we were looking at ages from between 10 to 20,000 years, possibly even larger than that. And so those glacial features being offset really well on top of the Aquarius Plateau gave a nice constraint for scarps that have happened at least in the last 18,000 years. So. Then again, running them through the MATLAB software was really helpful because it provided details that just weren't always visible on first glance in the LiDAR dataset. There were a couple areas with no data points, specifically the 10 to 15 kilometer stretch between Bicknell and the Aquarius Plateau. So you have like Boulder Mountain and Thousand Lake Mountain, but then the Fremont River runs straight through there. And then as well as the Fremont River, the whole fault zone is riddled with mass wasting events. And so there's a good example of just kind of some of the terrain that you see in the LiDAR in that zone. And so I found maybe one little viable piece there. And so what we did was take the average, the mins, maxes, and averages on either side of that and applied them to that particular stretch of the fault. And so we wanted to calculate moment magnitude. That was kind of the ultimate goal, was to get an estimate of the magnitude of the most recent event. And so the data set, pretty scattered. And so what we wanted to do was divide it into 5 kilometer segments and just calculate moment for each segment. And so we were able to do that and get an average, and that's how we filled in the gap there. And then taking the minimums and maximums for each 5 kilometer segment, we were able to calculate a minimum and maximum moment, a minimum and maximum moment magnitude, and then take the average. We used varying fault depths of the fault plane between 12 and 18 kilometers. This area is pretty close to some of the thinnest crusts in the basin and range, but at the same time has elevations all the way up to 11,000 feet and such a slow recurrence interval. So we wanted to get a wide spread of potential depths to that of the fault plane. So when we ran through just your standard moment magnitude equation, we're getting about 6.8. But when we broke it up into 5 kilometer segments, took minimums and maximums, we found ourselves still right between 6.5 and a 7 moment magnitude earthquake. And then again, that average of about 6.8. Wanted to compare that to some other studies that have been done in the basin and range, specifically the Wisnowski's 2008 paper, where he took a data set of basin and range papers and kind of came up with his an equation for calculating magnitude or moment magnitude simply using the length of rupture. And so when we put in that 32 kilometers of rupture into his equation, it gave us a 6.82. So right there together, pretty close, and was pretty happy with the range for an estimated moment magnitude. And those are my sources. Really quickly, I want to thank Dr. Toge for keeping me involved in these last few months. It's been a lot of fun to go back to this area. And that's my presentation. So, you guys want to come up here for questions?
5 or 10 minutes for questions.
Well, that's okay for David.
Yeah.
With your
Which
LiDAR
David?
David Johnson.
Oh.
You were showing with your LiDAR data of the entire rupture that the most recent activity was way south of I'm like, oh, that's.
Oh,
actually
yeah,
pretty
so
hard.
actually what I included is the whole length of the most recent was everything from the southern Aquarius Plateau up to just north of Bicknell, where you really lose track of anything that would fit into the data set.
It's
So.
just interesting showing the most recent activity south of the Lake Mountain.
Yeah, some of the most continuous scarps were down there on the Aquarius Plateau.
I'd like to ask the other David.
Yeah.
Had that anomaly in blue caused by crops,
Yeah.
did that affect the subsidence?
Not from what I saw. Not from what we realized. It didn't affect the subsidence because the areas of blue were really not in the subsidence areas. With the crops were, what we discovered, there wasn't any subsidence in those areas. It was mostly just the blue.
So those were crop circles?
Yeah. Crop circles, yeah.
Was there any way to filter that out?
Not from what I could tell. None. I didn't see a way to filter them out just from the data we had because it was just the differencing with that. So.
Okay.
So I don't know. I'm trying.
Is that uplift due to like all the watering? Is it maybe filling that pore space and causing the land to
It's
have
the
a
crops
positive
themselves.
No, they flew it when the crop was low one time, and then it was up.
Isn't the lidar filtering out that vegetation?
Like
Not
first return?
low-lying vegetation,
Oh, okay.
and it's not very high, it's
Oh,
just a
gotcha.
couple tens of.
So it is actually the crops, not anything of the soil or all the watering that's. Okay.
Yeah, that's the one thing to take away from this is the LiDAR, we say it's like maybe bare earth filtered, but it's not really. See some vegetation.
So those the kind of circles that are not there, like more like a hay,
Some
alpha,
pivot
those kind of vegetation.
Yeah, I was wondering too, the land cover where you saw the most subsidence, like what's the land cover like there?
Oh, over here now? It's
Yeah,
actually
over
interesting. Because now, what I've looked, is this is all like solar fields. So if you look now, it's all like, it's a whole solar farm, which I thought was interesting. And then like, there's like this major subsidence right here, but like, it was like meters of subsidence. And I just thought, because then there's like there's a little blue around it as well. Because there's a lake right here, so this is a lake, so that's where you get like those alluvial deposits right there. And so with this anomaly right here, I think it was construction. So I was trying to look at images on Google Earth and stuff like that, and I just think it was like construction and stuff like that. But now, it's just all solar farms, which is actually kind of interesting.
Is that the parallel gap that you're seeing right by that?
Where? Which one?
Right by your.
Yeah, it's that little
The
tree.
red left.
Oh, yeah.
No, keep going, keep
Just to
going.
the left of it.
Left.
Where is the parallel
Outside
gap?
of the.
You guys got a yeah, here, bro.
Okay, right there, right there.
Right here.
No, that,
The canyon.
Oh, yeah, yes, yeah. That's the parallel gap right there, yeah.
so are you saying that they're constructing right by the parallel gap now?
That's what it is, yeah. I mean, from what I saw on Google Earth, like, and when I was trying to like see what all this subsidence was, this was all just like solar farms now.
So you mean solar farms caused
No.
subsidence?
They built it on the subsidence.
You couldn't build
The
anything else
weight.
there.
They didn't build anything else. They did
Well, I'm asking because you guys are all interested in the geology. I'm interested in the indigenous rock art that's all down there, and if they're building there, it puts that in danger.
Yeah.
They've got
It's
a
in
lot
the
of it
valley.
fenced off really well.
Yeah.
Okay.
The dinosaur footprints, we gotta be worried about at that, man.
Yeah.
Okay.
So when you're talking about groundwater being like a cause for the subsidence, is it just like the people in the area like depleting the groundwater and like overusing water for like crops? Or I'm just wondering if you could go
Yeah.
more in depth.
Yeah, so like for agriculture, they're taking more from water out from the crops, and then also like the water treatment districts are just pulling too much from those things as well.
Okay, so is that just like creating negative space that's not supporting the topsoil?
Yeah, exactly. Yeah, that's exactly what's happening. Yeah, because they're taking out the water, so like it's creating like the cave. It's not a cave, but it's creating something like that. So it just subsides down into the ground because there's nothing to hold it up. So that's why it's creating like the earth fissures, like you saw in that one thing as well. Mhm.
A question for the Nephi follow people, I guess.
Okay, why don't you jump?
Do you want to pull up your figure of, like, your kind of major figure, I guess?
This one?
Next one, yeah.
This?
Yeah, so it's interesting to look at, because so you end up flipping the other author's paper, yeah?
Yeah, we flipped to Ross's figure.
Yeah, it is funny to look at this, right? So you can kind of see why DeRoss lined it up the other way, right? Because it's like, so to the left is to the south,
It's
right?
a little confusing, yeah, the way we oriented
So if
it.
any of you are confused,
That's why I
it's like,
was trying
if you were
to explain the
imagine you were
x-axis.
standing over on the west side of the valley looking at